In Level 4, we will be solving real-life applications of exponential growth and decay using the law of uninhibited growth or decay. In this formula, the A of t, or the output, represents the amount of a substance or population after time t. So, for example, if we wanted to know the amount of a substance that is left after 10 minutes, we might plug in 10 for t, and the output would be the amount that is left. A sub 0 is the initial amount, or that might be an initial population. K is the growth or decay rate. And that growth or decay rate in the formula goes in decimal form, but a rate is often expressed as a percent. And t represents time. Time could be in days, years, minutes, seconds, but the problem will indicate the units for time. In this first example, a colony of bacteria that grows according to the law of uninhibited growth is modeled by the function n of t equals 100 e to the 0.045 t, where n is measured in grams and t is measured in days. In part A, we need to find the initial amount of bacteria. And we find the initial amount just by looking at the formula. It's that number in front of e to the whatever. In this case, the initial amount is 100. And since n is measured in grams, that would be 100 grams would be the initial amount of bacteria, 100 grams of bacteria. The growth rate of the bacteria comes from the K value. In this case, K is equal to 0.045, but that's the rate in decimal form, and as a percent, that would be 4.5%. And I just found that by moving the decimal 2 places to the right or multiplying by 100. The population after 5 days, we take our formula and we plug in t equals 5. So n of 5 would be 100 e to the 0.045 times 5. Now, if you have a calculator that doesn't raise the exponent, make sure you put your whole exponent in parentheses. And that is equal to approximately 125.23 grams. And in part D, how long will it take for the population to reach 140 grams? In this one, we want to solve for t. And we know the amount at the end of that time period is 140 grams. So the amount after time t is 140. That is our output. So we set 140 equal to 100 e to the 0.045 t, and we are going to solve for t. To solve this equation, we first want to isolate the exponential part. So I'm going to divide both sides by 100. And we get 1.4 equals e to the 0.045 t. And then, so the first step was to isolate the exponential part. And now to, since t is in the exponent, I can take the log of both sides, in this case take the natural log of both sides, to cancel that e and get to the exponent. So I'm going to take the natural log of both sides. So step 2 is to take the natural log of both sides. And we get the natural log of 1.4 is equal to, well, the natural log and e essentially cancel. Really, the exponent moves to the front. Natural log of e is 1, and so we end up with 0.045 t. And then my last step is to isolate t, or solve for t by dividing both sides by 0.045. So step 3 is to isolate t. And finally, we want to plug that answer into our calculator. T equals natural log of 1.4 divided by 0.04, oops, lost a 0.045 is the decimal or the exact answer, but we want to get a decimal approximation by plugging that into the calculator, and we get approximately 7.48 days. Strontium-90 is a radioactive material that decays according to the function a sub t equals a sub 0 e to the negative 0.0244 t, where a sub 0 is the initial amount present, just like before, and a is the amount present at time t in years. Assume that a scientist has a sample of 500 grams of strontium-90. In part A, what is the decay rate of strontium-90? The decay rate comes from the K value, so K is negative 0.0244, but that is decimal form, and we want to give the rate in percent form. So we move that decimal, we multiply by 100 or move the decimal 2 places over, and it would be negative 2.44%. And because K is negative, it is exponential decay. In part B, how much strontium-90 is left after 10 years? T is equal to 10, and we want to find the amount after time t. So we need to write the function a of t equals, and the initial amount in this problem, it tells us that it has a sample of 500 grams. That would be the initial amount, 500. E to the negative 0.0244 t. And in this part, since we want the amount after 10 years, we're going to plug 10 in for t. So we want to find a of 10. So that would be 500 e to the negative 0.0244 times 10. And again, make sure if your calculator doesn't raise the exponent for you, that you have your exponent in parentheses. And plugging that into the calculator, we get approximately 391.74 grams. In part C, when will 400 grams of strontium-90 be left? We want to put 400 in for A of t, that's our output, and since it's saying when, we want to know what is t. We're solving for t. So 400 is equal to, we still have an initial amount of 500, so we're using the same formula, e to the negative 0.0244, and this time we don't know t. We're solving for t. So to solve this, we start off by isolating the exponential part. We divide both sides by 500, and we get 4/5 on the left side is equal to e to the negative 0.0244t. And now to get rid of that e and get to the exponent, we can take the natural log of both sides. And we get the natural log of 4/5 equals negative 0.0244t. And then our last step is to solve for t by dividing both sides by negative 0.0244. And t is equal to approximately 9.15 years. In part D, we are asked to find the half-life of strontium-90. Half-life is the time it takes for a substance to decrease to half of its initial amount. So half-life is the time it takes for a substance to decay to half of its initial amount. In this problem, we started off with an initial amount of 500 grams. So we want to know when it will decay to half that amount, or when A of t is equal to 250 grams. So we plug in 250 for A of t, because that's half of the initial amount. The initial amount is still 500. Same formula, e to the negative 0.0244t. And again, we will be solving for t. So we isolate the exponential by dividing both sides by 500, and we get 1/2 is equal to e to the negative 0.0244t. And notice that we will always get 1/2 in a half-life problem like this. It wouldn't even matter what the initial amount was, because the amount after time t is half of the initial amount. Okay, the next step is to isolate the exponential by taking the natural log of, or to get to the exponent and get rid of that e by taking the natural log of both sides. And we get the natural log of 1/2 equals negative 0.0244t. And then finally, we divide both sides by negative 0.0244. And we get t is equal to natural log of 1/2 over negative 0.0244. And plugging that into our calculators, we get t is approximately 28.41 years. So that means it takes about 28.41 years for strontium-90 to decay to half of its initial amount. The population of a town is growing exponentially. The population doubled in size over an 8-year period, and the current population is 25,000. In part A, we want to find the growth rate k for the exponential model. That means we should be able to figure out everything else besides k, so we can solve for it. We are told that the population doubled in size over an 8-year period. Assuming that trend will continue moving forward, 8 years from now, it would double again. So if the current population, or the initial population, is 25,000, the population after 8 years, n of 8, would be double that, which would be 50,000. So to find the value of k in part A, n of t is equal to 50,000, which is twice the initial or current amount of 25,000, and that will be the relationship after 8 years. So we're going to plug in 8 for t. And the only thing that is a variable is the k. So now we're going to solve for k. To do that, first we want to isolate our exponential. So I'm going to divide both sides by 25,000. And we get 2 is equal to e to the 8k. And now we want to solve for k, so we want to get rid of that e. We can take the natural log of both sides. And we get the natural log of 2 is equal to 8k. And then to solve for k, or isolate k, we divide both sides by 8. And we get k equals natural log of 2 over 8. In part B, we want to write the exponential model that models this population growth. So it's going to be n of t equals the initial population, which is the current population of 25,000, e to the, and now that we know k, we're going to leave it in its exact form, ln of 2 over 8 times t. And that is our exponential model. Now in part C, what will the population be in 3 years? We just want to plug in 3 for t. So n of 3 would be 25,000 e to the natural log of 2 over 8 times 3. And you want to make sure that whole exponent is in the exponent. You're going to need to close the parentheses on your natural log before you divide by 8 and multiply by 3. So plug that in your calculator and make sure that you get 34,421 approximately people. And finally in part D, after how many years will the population reach 80,000? So we set 80,000 is the amount after time t equal to the initial population of 25,000 e to the natural log of 2 over 8 t, and we're solving for t. So we divide both sides by 25,000, and we get 16 over 5 equals e to the natural log of 2 over 8t. And now that we've isolated the exponential, we take the natural log of both sides, and we get natural log of 16 over 5 equals natural log of 2 over 8t. And to solve for t, we're going to divide both sides by the natural log of 2 over 8. So t is equal to the natural log of 16/5 divided by the natural log of 2 over 8. And plug that into your calculator and make sure you get approximately 13.42 years.